Hey everybody, this is a continuation from the last video I made where I'm going over exercises that I did in yesterday's class on Monday, August 16th, 2021. This is an exercise from page 57. There are a couple of ways that we can do this. You may be able to do this exercise without seeing anything that I'm about to show you. However, there is a way to do this that involves a technique that we might not be aware of, and so that's why I'm showing it now. We're computing this limit, and of course, the first thing that we attempt is plugging in. So every place we see an x, we plug in 0. And we get 1/3 minus 1/3 is 0. And we get 0 on the bottom. And it's no good. Division by 0. So what do? We go to factoring and canceling, right? Okay. That's our second step. And before we go any further, let me point something out. This thing that we're looking at here is what we call a complex fraction. A complex fraction is a fraction whose numerator or denominator itself contains expressions that are fractions. And here the numerator contains 2 fractions, so we call this thing a complex fraction. And there's a way of simplifying this that we might not be aware of. So I'm going to tell you about it right now. The first thing that we do when we simplify complex fractions is write each denominator. Here's one denominator, 3 plus x. Here's another denominator, 3. And in the bottom, this thing does not have a denominator, but it's really the same as x over 1, isn't it? So we can say that this has a denominator of 1. The next step would be compute the product of these denominators. This won't always give us the least common denominator, but it will give us a common denominator. So let's see what we get. 3 plus x times 3 times 1. And this factor really isn't going to change anything. So what it really is 3 plus x times 3. And then the final step. Multiply the top and the bottom by this common denominator. Here's our common denominator. We're going to multiply the top. We're going to multiply the bottom. So here we go. Multiply the top by the common denominator. Multiply the bottom by this common denominator. And we're going to distribute this product to each term of the numerator and denominator. So we'll get 1 over 3 plus x times 3 plus x times 3 minus 1/3 times 3 plus x times 3 all over x times 3 plus x times 3. And a wonderful thing happens when we do this. Whole lot of canceling going on. And all of a sudden, we no longer have a complex fraction. We just have a numerator and a denominator. And forgive me, I should have inserted my limit operator. So let's see what we have. 3 and 3 plus x. And on the bottom, x times 3 plus x times 3. Three minus 3 is 0. Distribute this minus sign to the x. We have a negative x on top. And on the bottom, x, 3 plus x, and 3. And guess what? We can do some more canceling. And this is good. And I'll tell you why. Remember when we plugged in 0 for x to compute the limit? This was the factor. This was the factor on the bottom that caused us to get division by 0. So this is the factor that we want to cancel. And son of a gun, we got x in the denominator. We got x in the numerator. Zip, zip. We just got rid of the troublesome factors. We got rid of the troublemakers. So what are we going to do? Now we can plug in, right? We got rid of the troublemakers, the factors in top and bottom that were equal to 0 when we plugged in. We got rid of these troublemakers, so now we can plug in. I think I'll write that down. And we have 1 over 3 times 3, negative 1/9. Okay, there's our answer. We might as well do one more since we have the opportunity, a little bit more time. We did this one yesterday, and there are two ways that we can do this. We'll do it the way that we did yesterday in class. The instructions tell us to evaluate this limit looking at the graph. So they don't want us to compute this limit algebraically. They want us to compute this limit by looking at the graph of the function. And let's see. If x approaches 2 this way, how should I say this? As we move along the graph in such a way that x approaches 2 from the right, the y value gets closer and closer to 1. As we move along the graph in such a way that we approach x equal 2 from the left, the y value approaches negative 1. So is there any single value that this function gets closer and closer to as x approaches 2 from either direction? And the answer is no. As x approaches 2 from this direction, f of x gets closer and closer to 1. As a matter of fact, it's equal to 1. As x approaches 2 from this direction, f of x gets closer and closer to negative 1. As a matter of fact, it's equal to negative 1. So there is no one single value that f of x approaches as x approaches 2 from either direction. So we would say this limit does not exist. Now, if we saw the video that was assigned for homework last night, we can apply that knowledge to this thing and confirm what we've already said to be the case. Using the mindset from the video last night, we consider the one-sided limits. The limit as x approaches 2 from the left of this function, and as x approaches 2 from the left, the y value stays steady at negative 1. So this one-sided limit is equal to negative 1. Now, what about as x approaches 2 from the right? As x approaches 2, if we move along the graph in such a way that x approaches 2 from the right, the y value approaches and is actually equal to positive 1. So the limit as x approaches 2 from the right is 1. And we say the one-sided limits are not equal. And because the one-sided limits are not equal, this thing that we call the limit as x approaches 2 this thing that we call the limit as x approaches from either direction does not exist. Okay, that's what we did yesterday in class.